Welcome. We have here an infinite cylinder that is infinite in this direction and has a thickness t. So this is our side view of it. This is a kind of face view of it. But we're going to be thinking of where the charge density rho is not constant, that our rho depends upon the radius squared when r is less than the thickness, and then the charge density is 0 after that. So we could draw our rho versus radius as something like, right, a parabola going up, and then after t, it stays at 0. So if we have this infinite cylinder, an infinite cylinder has cylindrical symmetry. What we know from cylindrical symmetry is that our electric field is in the radial direction, so E is in the r direction, and is a function of capital R. So we can use r hat. And so what this means is we want to use a coaxial having the same axis cylinder as our surface. What does this mean? This means that we can draw a cylinder as a circle in this view. And then while our Gaussian surface is infinite, our cylindrical surface is not. So we are going to have, right, in this side view, our cylindrical surface would look like this, having some, right, z length L, and then some radius of this capital R. But this Gaussian surface is not complete because, right, it would only describe outside of the cylinder, what the electric field is outside of the cylinder. So we also need to think of another one inside of the cylinder. So, right, also L, and then this being R. Why do we choose a cylinder? Why do we have to choose a cylinder for our cylindrical? It's to make this part of Gauss's law be a lot easier. So when we were doing Gauss's law, we kind of split this along the center between our left-hand side and right-hand side. So on this left-hand side, we have that our closed integral of E dot dA is equal to the integral over the tube of E dot dA plus the integral over each of these individual caps. So why am I not doing too much with the left cap and the right cap? Well, that's because we know that our electric field has to be in the radial direction, which means it's pointing out in this way here, means it's pointing out in this way here, but it also means it's pointing out in this way here. Whereas our dA for, right, this tube section is doing fine, but our dA for these sections are doing no good. So the reason we've chosen this cylinder is that now this left cap and right cap are 0 because our E is perpendicular to dA for this section. And then if we are a function of r along this tube, our radius doesn't change, so we can pull the electric field over the tube out of the integral, and then we get E of the tube times the integral of dA of the tube. And so then we just get the electric field at our tube, right, as a function of the radius of the tube, times the area of the tube, right? dA of the tube is just area of the tube, and the area of our tube is 2 pi RL. So everything's nice with this side, right? If we choose the right Gaussian surface, then this whole side becomes very, very easy. Over here on this Q enclosed over epsilon naught, let's look first at inside the cylinder. Inside the cylinder, our Q enclosed is equal to the integral of rho enclosed times dv, and we integrate up to our r. So we integrate from 0 to capital R. Well, so then we plug in our rho for this. So we have the integral of CR squared. Our dv for the tube part is going to be 2 pi RL dr, capital R, capital R. So from 0 to R, see what constants we have inside of here. We have C, we have 2 pi, we have L, so we have 2 pi CL, and then we have the integral from 0 to R of R squared times R is R to the third times dr. So then our Q enclosed over epsilon naught is 2 pi CL R to the fourth over 4. For R outside the cylinder, let's use a bit better of a marker. Outside our cylinder, we have that our charge enclosed is going to be the inside charge density dV, and we are going to capture all of it, so from 0 to t. And then we have to finally end at R, and so we start from t to R of our charge density outside, and in this case it's 0 dV. So if we have a definite integral of 0, this becomes 0, nicely enough. So this is then the same integral as this one, except instead of from 0 to R, it's 0 to t. So our Q enclosed over epsilon naught is going to be 2 pi CL t to the fourth over 4. So now we have inside the cylinder, outside the cylinder, and we have our Gauss's law. So then we can look at what's going on in there. So we have inside our cylinder, we have E as a function of R times 2 pi RL is equal to our Q naught over epsilon naught. We divide by epsilon naught. Divide by epsilon naught is 2 pi CL over epsilon naught R to the fourth over 4. So bringing these all together, we have then, we can cancel out the 2 pi on each side, the L on both sides, which means our choice of how long of a Gaussian surface we have does not matter. And then this R, we can actually cancel out this with 1 power of our 4 powers there. And so we get that our electric field as a function of R is C over epsilon naught R to the third over 3, so we usually put a 3 there. And then we know that our electric field has to be in the radial direction, so we put this capital R hat. So this is for R less than T. Similarly, we can look outside the cylinder. And so we bring our same result from here. E is a function of R times 2 pi RL. And now we have our Q enclosed over epsilon naught is 2 pi CL over epsilon naught T to the fourth over 4. We get some canceling, not as much as we had. The 2, the pi, the L, the 2, the pi, the L still cancels. But now this R doesn't cancel with T, and so we have that our electric field as a function of R, we can give ourselves a little, is C T to the fourth over 4 epsilon naught R hat. Excellent. One last step that we can do is we can take a look at our electric field as a function of the radius. And so we have inside the cylinder before r is equal to t. This is r to the third power, so we'd have some increasing function. And then after r greater than t, we have down here that we have 1 over r. So we would have it be starting to decline a little bit like that. So just to notice, right, even though our charge density is 0 past here, our electric field will not be 0 until we get all the way out to infinity.